After watching this video lecture, students will be able to differentiate between average and instantaneous rates and calculate average and instantaneous rates from experimental data. So kinetics is going to be directly related to something called the reaction rate. Now, the reaction rate is the specific speed at which a chemical reaction occurs. And depending on the reaction that you're observing, you're going to observe different rates or different speeds. If we look here, we have an explosion that happens very quickly, versus over here on this end, we have an erosion process that takes millions and millions of years. So different chemical reactions are going to have different reaction rates. Chemical kinetics is the study of these reaction rates. Now, chemical kinetics can help us delve more deeply into our understanding of what's happening at the molecular level. So the reality of it is most reactions do not occur by single-step reactants to products as we have written here in this overall reaction. The reality of it is they usually occur through multiple steps. And these multiple step processes are known as reaction mechanisms. Now, the analysis of specific rates of specific reactions can help us determine a plausible reaction mechanism. And analyzing these rates allow us to kind of understand on a more molecular level what is happening during a specific process. Now, we will talk in great detail about reaction mechanisms and the writing of reaction mechanisms in future video lectures, but for right now, I want you guys thinking and starting to think about the molecular level interaction between our reactants in specific chemical processes. Before we get into the details of reaction rates and the things that can affect reaction rate, let's go ahead and let's look at the basic requirements associated with reactions actually occurring. So in order for reactions to occur, there are two requirements. The first of which is the fact that molecules must collide with sufficient kinetic energy in order to break bonds. Okay, so we know that in order for products to be formed, we first must basically disassemble or break bonds within the reactants. So if we go ahead and look at this unbalanced chemical equation here, what we notice is that we have carbon bonded to hydrogen and oxygen bonded to oxygen on our reactant side. Now, if we look at our product side, we notice that we have carbon bonded to oxygen and oxygen bonded to hydrogen. So the reality of it is that the only way to get the products to be bonded in this manner requires us to first basically disassemble or break apart the bonds within the reactants. Those broken bonds will then reassemble into the products, and you'll subsequently get the reaction that we see here. However, in order to break these bonds, enough kinetic energy has to be present for that to actually happen. So energy has to be put in order to break up these bonds, and then depending on the formation of products, that will dictate the overall enthalpy change associated with this reaction process. So if we have enough kinetic energy to make the first requirement satisfied, we then move on to the second requirement. Now, if we go ahead and look at the second requirement, which states that molecules must collide in a specific or correct orientation for new bond formation to actually happen. Okay? So we're going to go ahead and look at this generically with respect to this reaction here. So if we go ahead and we look at this particle diagram, what you see here is an NO molecule and an O3 molecule. The NO molecule has its nitrogen atom pointing down, and it's directly across the way from one of the oxygen atoms in the ozone molecule. Okay, so if these two are able to bump into each other with enough kinetic energy, the nitrogen here is going to be able to interact with the oxygen molecule here. That will produce our NO2, and we'll be left over with the two remaining oxygens with ozone. Now, obviously, I'm showing this diagram without any breaking up of the molecule here, just to show a simplified version of this thought process. Now, if we look at this from another particle diagram or another position in terms of orientation, we'll see a very different result. So as you can see here in this diagram, the NO molecule is oriented in a different orientation than we saw over here on the left-hand side. And notice that oxygen atom from the NO is across the way from the ozone's oxygen atoms. In this context, even with sufficient kinetic energy, the orientation would not give us the appropriate bond that we would desire. We do not want a bond to form between the oxygen atom and the NO and an oxygen atom from the ozone. We want instead for the nitrogen atom to be bonding to one of these oxygens. So in this context, this orientation, even with sufficient kinetic energy, will not give us the desired reaction. So what will happen is these molecules will bump into each other and continue on their way without any bond formation occurring. So now that we understand the two requirements for getting a reaction to occur, let's go ahead and talk about the four factors that affect reaction rates. Now, as we discussed previously, molecules of the reactants are bumping into one another, and they have to have the correct kinetic energy and the correct orientation in order for those reactions to actually happen. So the more collisions that we have in a chemical reaction, the more likely we are to have the two requirements met. So typically, the more collisions you have, you're going to see an increase in the rate of your reaction. So we're going to discuss these four means of increasing the rate of reaction. So the first one we're going to talk about is physical state. So there's going to be two types of reactions that we're going to look at. We're going to look at homogeneous reactions and heterogeneous reactions. So the physical state of the reactants in a homogeneous reaction are going to be consistent. So they're either going to be liquid-liquid or gas-gas. So the reactants are going to be in the same phase. Now, a heterogeneous mixture or heterogeneous reaction is going to have usually a solid and either a gas or a liquid. Okay, so the phases of our reactants are different for these two types of reaction processes. Now, what you may notice is that in the case of homogeneous mixtures, all of the particles are able to just kind of mix and are dispersed amongst each other. In the case of heterogeneous mixtures, you definitely have a limitation of the interaction between the particles due to there being a solid phase surrounded by a liquid or a gas. Okay, so heterogeneous mixtures are going to be limited by the surface area of the solid. So in order to alleviate this drawback, what you can do is actually break up the solid into smaller pieces and create a larger surface area in that solid. And by creating a larger surface area, what ends up happening is the particles of the gas or the solid can then be interspersed between the solid particles, and you have more chances for interactions to occur, which of course potentially leads to a more rapid reaction. Now, the next or the next factor that we're going to talk about is reaction concentrations. Now remember, more collisions are going to usually correspond to an increased rate. So if we have one container that has a small concentration of the reactants versus one that has obviously a much higher concentration of reactants, you're going to get more collisions in the reaction container containing more reactants. So in that case, the reaction container that has a higher concentration of reactants is typically going to experience a higher rate of reaction than those that have less. So for most reactions, if you increase the concentration of your reactants, you're going to increase your reaction rate. That brings us to our third factor, which is going to be reaction temperature. Now, as you increase your temperature of your reaction, you end up increasing your kinetic energy. Okay, and as you increase your kinetic energy, you end up allowing more collisions to occur. More collisions typically lead to an increase of rate of your reaction. So, in most cases, an increase in temperature is going to increase the reaction rate. Now, this brings us to our fourth factor, which is going to be the presence of a catalyst. So, a catalyst is an agent that gets added to a reaction mixture that's going to increase the rate of the reaction without actually being used up. And the way that it does this is that it adjusts or alters the reaction mechanism. So it may alter collisions or basically change orientations or isolate orientations that help facilitate better reaction probabilities and subsequently leads to basically an increase in the rate of your reaction. And we're going to talk about catalysts in more detail a little bit later, but these are the four factors that you need to know and understand with respect to their effect on your reaction rates. So there are two ways that we're going to be looking at rates of reactions. We're going to be looking at them based on their average rate or their instantaneous rate. And we first want to define the difference between these two before we go ahead and analyze each with respect to collected experimental data. So average rate is the rate of a reaction over a specific period of time. Now, the average rate is going to be represented by the change in the concentration of either a product or a reactant divided by the change in time. Now, the concentration and the time period are obviously directly related and obtained from experimental data. So calculations-wise, what we're going to do is we're going to take the concentration of our reactant or product at the final time in terms of whenever we're stopping our analysis minus the concentration of our reactant and product at the initial time that we start looking at. Now that's going to be divided by the difference in times final minus time initial. Now typically speaking, guys, your concentration and your times are going to be in molarity and seconds respectively. Okay, so please make sure that you're paying attention to units. Remember these concentration brackets here refer to the molarity. The time here is typically going to be seconds, although please make sure that you're keeping an eye out with respect to the units of time, especially because sometimes they'll put it in minutes or hours depending on the rate of the reaction. So now that we understand the average rate and kind of how that's looked at, we're going to go ahead and talk quickly about instantaneous rate. Now, instantaneous rate is the rate of a reaction at a specific point in time. Okay, so unlike average rate, which is comparing the change in the rate over a specific time period, the instantaneous rate is looking at the rate at a single point in time. Okay, and basically what we need to do here is we actually have to graph the data from our reaction. Okay, and basically what we need to do is we're going to end up taking a line tangent to this curve that we produce from our rate data. Okay, and basically our instantaneous rate is going to be established from the slope of the line tangent to the curve, and we're going to talk about how we go about doing that in a little bit here. But what I want to point out, guys, is average rate and instantaneous rate are different from one another. And the reason why is because the rate of a reaction is going to change as the reaction progresses. The reason why is because as the reaction progresses, the amount of your reactants is going to decrease. And as the amount of your reactants decrease, obviously your collisions decrease, and you subsequently are going to have a slower reaction because less collisions are occurring. So with that in mind, let's go ahead and let's look at some calculations and analysis of data for both average and instantaneous rates. Okay, so we're going to go ahead and we're going to look at the average rate with respect to this equation right here. And we're going to utilize some data here to help us with that. So notice we have our time data set in seconds. We have the concentration of our reactant as the time progresses. We have the concentration of our products as time progresses. So what I want you to notice here is that initially we start with some reactants and no products. And as time progresses, the amount of our reactants decrease and the amount of our products increase, which is, of course, what we would expect for any type of reaction. So the average rate of NO2 is going to be written as the change in NO2 divided by the change in time. Okay, so if we go ahead and we're going to look at this between the time equals 0 and the time equals 50-second time slot. So when we go ahead and we look at that, we're basically going to be taking the concentration at time equals 50 minus the concentration at time equals 0 and dividing it by our time 50 minus our time 0. So that's going to give us the following setup where we have our concentrations from our table divided by our time. After plugging this into our calculator, we're going to get negative 4.2 times 10 to the negative 5th molarity per second. Okay, so this is the rate associated with NO2 being converted into NO and O2 for this particular time frame. Okay, now what I want you guys to notice is that we have a negative sign here for our rate. And if rate is referring to how long something takes, we don't usually think of time with a negative context. So what I want you guys to change over in your head is the fact that we have to consider what's happening physically to reactants versus physically to products. Reactants are being used up, so they are disappearing while products are appearing. So in order to facilitate not having negative signs for our rates, we have to make an adjustment to the rate expression for our reactants. And really, this is just a mathematical adjustment so that we're not dealing with the oddity associated with having a negative rate. So our rate law for our reactant will have this negative sign in front to make that adjustment. So our rate for the reaction over the time frame that we discussed above will be the following value. So another way to express this rate is that we refer to it as the rate of disappearance of NO2 over this specific time frame. So earlier when I was discussing the instantaneous versus average rates, we talked about the fact that the rate of a specific reaction is not going to be constant over time. In fact, it's going to change. And the reason why that's the case is because we're obviously going to have less collisions when the quantity of our reactants decreases. Okay, so if we look at this curve here, this is the disappearance curve for our NO2. So notice, this is our time, this is our concentration. As the reaction time progresses, the concentration of our reactants is going to decrease. And what we see if we do our calculations for specific time frames is that we have a decrease in our rates as the concentration of those reactants also decrease. Now in that same thought process, these are the curves associated with the production of our products, NO and O2. And as you can see, as the time progresses, the quantity of these products is going to increase with respect to their concentration. Now, in the same way that our rate of our reaction is going to decrease with respect to the disappearance of our reactant, the rate of appearance of our products is also going to decrease as those collisions decrease, because the appearance of our product is dictated by, the collision process that's happening for our NO2 molecules. So instantaneous rate is going to be calculated from the graphical analysis of specific points on our curve. Okay, so we have this curved line here that's representing obviously the decrease in the concentration of our NO2 reactant over time. Okay, and if we want to know the instantaneous rate or the rate of the reaction at a specific point in time, what we're going to do is we're going to draw a line tangent to that specific point. We are then going to take the rise and the run associated with the slope of that line, and that's going to allow us to calculate our instantaneous rate. Okay, so we draw this line tangent, okay, we get this rise, we get this run, and we plug it into the rise over run situation that we see here. We plug those numbers in, divide them in, okay, and we calculate our instantaneous rate, which at this particular point in time is going to be 2.36 times 10 to the negative fifth molarity per second. Okay, so that is the rate at that instantaneous point in time. Now remember, this is very different than the average rate, which is the rate associated with a specific time frame instead of a single point in time. So one is an average and one is just a specific value associated with one time frame. So the last thing we're going to look at in this lesson is the effect that stoichiometry has on basically the way we look at the reaction rates of specific components of a reaction. So if we look at NO, okay, and NO2, the relationship here is 2 to 2 or 1 to 1 in terms of mole ratio. Okay, so the production of NO is occurring at the same rate as the breakdown or decomposition of NO2. Okay, the stoichiometry supports that. Now, O2 is also a product that's being produced, and in this case, O2, right, is going to be produced at half the rate that NO2 is consumed. Okay, another way to look at this is that the rate of NO2 consumption is twice that of O2 production, right? We have 2 to 1 ratio here. Okay, so in order for us to basically relate our reaction rates, our average reaction rates, okay, we need to look at the stoichiometry associated with the specific reactions. So let's go ahead and let's take a step back and let's first look at the 1-to-1 relationship. Okay, so So we know that the average rate of a reaction is going to be related to the change in concentration of whatever substance we're looking at divided by the change in time, right? Okay, so we've already done those calculations. We've already looked at how that works. Now, okay, we know that we're going to have a negative sign in front of the average rate, okay, formula here for the decomposition of NO2 because NO2's concentration is decreasing over time, so any changes we have here are going to have a negative value, so we need to make an adjustment for that value. Okay, now the rate of the breakdown of NO2 is going to be equal to the rate of breakdown of NO, and we know that because the mole ratio is 1 to 1. Okay, now if we think about this with respect to how NO or NO2 are related to the production of O2, we have to consider the stoichiometry once again. So if we look at the relationship between, say, NO and O2, the relationship is 2 to 1, okay? Or we could look at this as being 1 to 1/2, right? Okay, so basically the production of O2 is occurring at half the rate of the production of NO, okay? So in order for these rates to match up, okay, I would need to double the rate of the production of O2 to match the rate of production of NO or NO2 respectively, okay? So this is a little bit weird, and we have a way that allows us to simplify this thought process. So let's go ahead and let's look at that so we don't have to mess with the difficult aspects. Okay, so we can simplify what we just saw on the previous slide. We're going to continue to look at this same equation, but what we're going to do is we're going to utilize this relationship between our reactants and our rate laws and the stoichiometry that's presented in the equation. Okay, so the lowercase a, b, c, and d, okay, that's going to correspond to these values down here. Obviously, the lowercase a is going to refer to the rate law associated with reactant A and B, etc., etc. Okay, so how are we going to go about writing our rate law for our equation here? Okay, well, first of all, guys, we know that NO2 is a product or is a reactant. Okay, and since NO2 is a reactant, we know we're going to have a negative delta NO2, okay, over delta T. Okay, now because of the stoichiometry, we're going to go ahead and take the coefficient of 2, and that's going to be in the place of A here. Okay, so if we go ahead and plug that in, so that gives us our rate associated with the disappearance of NO2. Okay, and that's going to be equal to the rate of appearance of NO. Okay, now NO is basically in that 1-to-1 relationship. Okay, so it's going to have the same rate expression in terms of the values down at the bottom, but obviously it's going to have a positive sign because the NO is appearing. Okay, and lastly, of course, guys, the rate of appearance of O2 is going to be positive, and because our coefficient in front of the equation, or in front of the O2 molecule, is 1, we're just going to have delta T down below here. Okay, so this is how each of the rates are related to one another. Okay, so basically, the rate of appearance of O2, right, is going to occur at half the rate of the appearance of NO, or half the rate of disappearance of NO2. Now this looks slightly different than what we saw on the previous slide, but really the only difference is that instead of looking at it as being the rate of appearance of O2, we related the last slide's information to the rate of disappearance or the rate of appearance of NO. So basically what we did is we multiplied all these through by 2 to get rid of the fractions here and basically give us a coefficient of 2 in front of this number. So this is an easy way to write the rates for stoichiometrically related substances without having to think too hard and long about each of them and their relationship. Okay, so we're going to utilize this general equation and these general relationships to get our rates. So let's go ahead and let's apply what we just learned. Okay, they want us to dictate how the rate at which ozone disappears is related to the rate at which oxygen appears. Okay, so we have a balanced chemical equation here. We have our relationship that we know. So what we're going to go ahead and do is we're going to write our simplified rate laws, and we're going to start first with the ozone. Okay, so ozone is going to disappear, so we're going to have a negative value. Delta is going to be related to that change of the ozone molecule, all divided by 2 delta T. Okay, and the reason why we have that 2 is because the coefficient in front of our ozone is going to be equal to 2. Okay, in that same way, that's going to be related to the rate of appearance of O2 by the following. So we take our change in our O2 divided by 3 times delta T. Okay, and that is our relationship. Now, to help simplify this, we are going to look at just the rate law associated with the disappearance of ozone. Okay, so we want to get this all by itself. So in order to do that, we're going to multiply both sides by 2. So once we've multiplied both sides by 2, that gives us the following expression. And what this expression tells us is that the rate of disappearance of ozone is going to be equal to 2/3 the rate of appearance of O2. And those are obviously numerical values that we can relate to a little more easily. But basically, a small manipulation and isolation of the rate expression for that specific substance will allow us to make this an easier assessment. So let's go ahead and apply this in a different way. So they told us that if the rate at which oxygen appears is 6.0 times 10 to the negative fifth molarity per second at a particular instance, at what rate is the ozone disappearing at this same time? Okay, so basically they've given us an instantaneous rate for the appearance of our O2 product. And they want us to tell them the instantaneous rate of disappearance for our ozone at that same time frames. Okay, so what we're going to do is we're going to utilize the relationship that we just wrote on the previous slide. So this is our expression that we were able to establish on the other side. Now, the instantaneous rate of the disappearance of O2 is going to correspond to this area of our rate expression. So what we're going to do is we're going to plug in our numbers there. And that plug-in will look like this. So guys, I want to point out very clearly, okay, so your rate of disappearance of your ozone is equal to this expression. It's going to be equal to 2/3 of the rate of appearance of your oxygen. Okay, so I want you guys to understand that the combination of the change in concentration over the change in time is equal to the rate of those particular species for this reaction. Okay, so what we're going to do is we're going to go ahead and plug these numbers into our calculators. We're going to take 2/3 times 6.00 times 10 to the negative fifth, and that's going to give us 4.0 times 10 to the negative fifth molarity per second. Okay, and so that is the rate of disappearance of ozone relative to the appearance of oxygen. Okay, so the rate of disappearance of ozone is going to be 2/3 that of the rate of appearance of oxygen.